Computer music interfaces by using JUCE. This presentation is about my research master's project that I've been developing over the past 1 year. My supervisors are Professor Eduardo Miranda and Dr. Edward Brown. It is being developed in the Interdisciplinary Center for Computer Music Research, ICCMR, in the University of Plymouth. So conventionally, for us to control any sort of computer interface, we require muscular power in some form or the other. For example, controlling a mouse cursor with the help of a mouse, or typing in text with the help of a keyboard, or even using devices that recognize your speech. Brain-computer interfaces, also known as BCIs, aim to provide a communication medium that is independent of muscle control. So the way this is done is that you have a one-to-one function between the brain waves and the output produced by the system. So you have sensors that detect brain waves, you have signal processing algorithms that analyze brain waves, and you have a corresponding output that is generated by the computer. One immediate application of this technology is that it is beneficial for patients who are suffering from motor disabilities. Locked-in syndrome is a condition that causes the loss of all or most motor abilities. This can be caused due to diseases like amyotrophic lateral sclerosis, spinal cord injury, or even stroke. So as you can see in the pictures, there are two different applications of brain waves. On the left you have of BCIs, of brain computer interfaces. On the left you have a BCI based video game where a user controls a character within a game with the help of a BCI, and on the right you have a locked-in syndrome patient who is able to drink coffee with the help of a robotic or a prosthetic arm. In this project, we detect brain waves through electroencephalogram, or popularly known as EEG. Brain-computer music interfaces are basically BCIs that can be used for musical applications such as performance and composition. Now BCMIs can be classified into two different categories. You have passive control BCMIs and you have active control BCMIs. So passive control BCMIs is where you have an indirect relationship between the brain waves and the output produced by the system. An example of such a passive control system is sonification, and you can use it for applications like emotional alerting, where you can generate one sound if a person is feeling happy, and you can generate another sound if a person is feeling sad. The problem with passive control systems is that the user is not given complete control over the output produced by the system. So in this project we explore active control, and in the subsequent slides I'll be telling you how active control is achieved by this project. The first motivation for BCMIs is that it provides novel pathways towards performances. Generally when we control a musical instrument or a musical interface, we generally play it with our hands, or we use our feet in some cases, or even our mouths for wind instruments. So BCIs provide novel pathways or a new mechanism to control a musical interface. The second motivation is to allow patients with motor disabilities to experience the realm of music technology, and so to build tools like composition tools would provide a way for such patients or such individuals to release their creativity. As you can see in the picture is an earlier BCMI system developed in ICCMR, where locked-in syndrome patients were allowed to choose musical phrases, and these were played by an external musician. The first objective of this project is to make BCMI technologies more usable for practical deployment in real-world scenarios. There is a huge gap between BCI research conducted in labs and it being deployed in actual real-world scenarios. So you have very sophisticated sensors and equipment that detect brain waves, which are often bulky, and they comprise a lot of wiring, and they're not suitable for real-world applications. So this project aims to use less sophisticated sensors that would be more portable and are also wireless in nature. The second point under this objective is the deployment in commercial platforms. So, earlier BCMIs generally use bespoke hardware and dedicated microcontroller boards that run BCMI based operations. This project would aim to deploy brain computer music interfaces into commercial platforms like laptops, tablets and mobile phone applications. The second objective is to improve communication rates. Generally in like conventional computer interfaces are very different from BCMIs. Like for example, you want to increase the volume in a musical interface, you just turn a knob. But in BCMIs this is not that simple. Like we are at a stage where a user can make choices, can make binary choices from an array of different buttons. So, the rate at which the user can communicate with this with the interface is very slow, and hence there is extensive research conducted to improve the communication rates. Now generally such technologies are built in high level programming languages like MATLAB and Python. The reason why I ended up choosing JUCE or a C++ application framework to build this project is to make a standalone BCMI system. So, earlier BCMI generally used separate processors because they are computationally very expensive, and also as I mentioned earlier, one of the objectives of this project is to move this technology from labs to real world scenarios. So, exploiting the ubiquity of platforms like mobiles, tablets and laptops for BCMIs would be a suitable good option to explore. So, as I mentioned earlier, this project aims to achieve active control, and the way this is done is it uses a paradigm called steady state visually evoked potential, and is also popularly known as SSVEP. As you can see in this animation, you have different flashing regions, and each of these regions flash at a unique frequency. So, the top left region is flashing at 6 hertz, then the next one is 6.6 and they are equally spaced at 0.6 hertz, and the last one is flashing at 9 hertz. So, the thing is, when the user is gazing at a specific frequency, the corresponding frequency or the same frequency is triggered in the user's brain waves, and since it's being triggered in the user's brain waves, you are providing you're providing active control to the user, where he can make choices from a screen by just looking at them. So, yes, so this is the paradigm steady state visually evoked potential, and this project adopts this technique, and this is the overview of the system. The first operation is a visual stimulus. As you saw in the previous slide, you have different flashing regions that flash at unique frequencies. The second the step is to detect EEG signals, and so as mentioned earlier, electroencephalogram is a technique of detecting brain waves, and the next you analyze brain waves. An analysis like you have different signal processing techniques that analyze brain waves, and then you have a corresponding output that's generated by the computer. So, earlier BCMIs used microcontroller boards to present the visual stimulus. Like on the right you can see a square wave, and each flashing region was flashing at a unique frequency. Now, the problem with square waves is that if you are deploying it in commercial platforms, you are limited by the monitor refresh rate. So, when you are using LED bulbs to present the visual stimulus, you do not have this problem. So, in 2013, a scientist called Manyukov proposed sinusoidal stimulation, where the region gradually turns on and gradually turns off. So, earlier the problem was using square wave stimulation on a monitor of 60 hertz. You could only present frequencies like 15, 12 and 10. The monitor refresh rate needs to be divisible by the stimulation frequency, but after sinusoidal stimulation was proposed, the number of flashing regions on the screen could be increased, And so to realize SSVEP on a commercial platform, we will require hardware accelerated rendering and vertical synchronization, which is achieved through OpenGL in JUCE. So in this project, we have used a wireless and dry EEG headset to detect brain waves. As mentioned earlier, BCI research, generally in BCI research, they use medical grade headsets that use sophisticated sensors, which require a lot of setup time and which are not practical for real world scenarios. So in this project, we are using a dry and wireless EEG headset that's manufactured by Cognionics Incorporation. So on the left, you have a picture of the headset, and in the middle, you have a picture of it being deployed on a mannequin. And on the headset is powered by Bluetooth. So you have the headset recording EEG data, and it transmits data over Bluetooth, and it's received by a USB dongle. So in the future, when we aim to deploy BCMI technologies on other platforms like tablets and laptops, so we need to get rid of the Bluetooth dongle and develop a separate driver to receive EEG data. Now, so in the earlier slide, you saw SSVEP exploited frequency domain characteristics in brainwaves. So the most straightforward way of analyzing SSVEP would be a simple power spectral density analysis. But unfortunately, the EEG is not similar to audio signals, where in audio signals you have a very good SNR, you have very good signal quality. So power spectral density analysis carries out very well. But in EEG, the SNR is very poor. And so instead of simple PSDA, alternative signal processing techniques such as statistical signal processing techniques have been proposed in BCI research, and I'll be talking about that in the next slide. Another interesting phenomenon is the harmonic frequency components in SSVEP. So suppose a user is gazing at 6.6 hertz. Along with 6.6 hertz, you will also have 13.2, 19.8, and 26.4 hertz. Like, you have different harmonics that are detected in the user's EEG. And it is important to note that these harmonics are not a consequence of the visual stimulus. It is a consequence of SSVEP. So it is a phenomenon that is observed in SSVEP itself. And furthermore, I mean, again, the number of harmonics that will be detected in EEG depends on how good the EEG sensors are and how good the SNR is. As mentioned earlier, this project uses statistical signal processing techniques, and a multivariate statistical technique called canonical correlation analysis is used in this project. So this statistical procedure quantifies the correlation between two different variables. So it's like you're recording audio data from multiple microphones. So you have data recorded from multiple microphones, and you quantify the relation between the recorded data and reference signals. So on the X matrix, you have EEG data recorded from 4 different electrodes. That's labeled as E1, E2, E3, and E4. So in conventional PSDA, you just have a univariate analysis between one variable and another variable. But over here, we have a multivariate analysis where you check the frequency components of the reference signal along with data recorded from 4 different regions. And research has proven that this technique is much more efficient than PSDA for SSVEP based systems. And on the Y matrix, you have sine and cosine waves of different harmonics, and we conducted tests to find that 5 harmonics is the most efficient number of harmonics for analyzing EEG. When the number of harmonics was greater than 5, it was, I mean, there was no improvement in performance, so 5 seemed like the optimal number. So each of the flashing regions, like the 6 different flashing regions, have unique frequencies. So you have sine and cosine waves of the first harmonic, you have sine and cosine waves of the second harmonic. So the number of columns in the matrix would be 10, corresponding to sine and cosine waves of each harmonic. And so CCA requires, adopts complicated mathematical operations like singular value decompositions and calculating inverse square roots of matrices. So Eigen, which is a C++ template library for linear algebra, was used by this project to implement CCA. This video is a demonstration of me playing the BCI, and so there are 6 different regions, and each of the flashing regions corresponds to notes of the minor pentatonic scale, and I will be playing the notes in ascending order. So that was a simple demonstration of me using the BCMI. So in order to test the universality and the robustness of the system, we conducted experiments on 6 different subjects, and 3 were experienced with using BCI technologies and 3 were inexperienced with the technology. There were some interesting observations made in the EEG recordings. One was we observed a huge peak of frequencies that are under 1 Hertz. So the low frequencies, like the global maxima of the graph, is somewhere under 1 Hertz, which is pure noise. And as I mentioned earlier, the SNR of EEGs is pretty poor, and so we observed a huge peak of frequencies under 1 Hertz, and we also observed a peak at 50 Hertz, which is actually an unusual observation for wireless systems. So filtering was done to improve the SNR of these systems, and in this slide you can observe the performance of with filtering and without filtering. Like, there is an improvement in accuracy of the system. An important point that I forgot to mention earlier is that in BCI research, there is often a trade-off between speed and accuracy. So as you're giving more time for the system to recognize the choice of the user, the accuracy improves. So that's like a time versus accuracy graph, where the accuracy gradually improves with time, and at 2.5 seconds you can observe it kind of surpasses 90% accuracy, and beyond 2.5 seconds there's not a significant improvement in accuracy. So the optimal window for analyzing EEG data was 2.5 seconds, and so in order to implement the filtering, the thing is, like fire filters wouldn't be a practical solution, as the frequency to obtain a good enough frequency resolution would require high computational complexity, and but on the other hand, while implementing IR filters, we would end up having nonlinear phase and phase distortion. So because of that, zero phase filtering was implemented, where you filter the signal forwards and you also filter the signal backwards. So that way you end up having zero phase distortion. So zero phase filtering was implemented in this project for filtering EEG data. And these are the individual results of different subjects. So each subject, 5 out of 6 subjects obtained an accuracy of greater than 90%, but one of the subjects obtained an accuracy of less than 80%. So further research needs to be conducted on making the system more universal for all users. And so future work would encompass cross-platform deployment. So right now the system was deployed on a laptop. So now extending this technology to other platforms like mobile phones and tablets we would end up encountering a lot of challenges because the size of the flashing region is much smaller. So it subtends a smaller visual angle with the user, and also the flashing regions would be they would be closer to each other. So that way we would obtain less classification accuracy. And this is a small video demonstration of SSVEP on a mobile phone. And in the future, also like a bespoke control flow would be developed where you have a multi-screen BCMI. So one screen would allow the user to choose a musical instrument, and the next screen would allow the user to actually play the musical instrument. So in order to make the system more interactive, I used OpenGL textures, and so I loaded all the textures, all the different icons into one single image file, and I just mapped the texture coordinates accordingly. And in future, as mentioned, one of the subjects out of the 6 subjects obtained a lower score of accuracy and lower performance. So machine learning algorithms would be explored in order to improve, in order to explore subject-specific performance and improve the robustness of the system. Hope you guys enjoyed the presentation. Thank you.
Thank you very much. We have a few minutes for questions. Any questions?
So I've seen in the past people try to do the same with eye tracking. How does that compare to your thing? Yes, eye tracking is they're very different fields. So there are advantages over eye tracking, and there are disadvantages over eye tracking. So one is eye tracking requires calibration, and so BCMIs do not require calibration. That's one. The second thing is so in this project we are using wireless and dry EEG. So when you're using like medical grade equipment and laboratory based equipment, the quality of signals are much greater. So you end up, I mean, there are researchers who have obtained a latency of as low as 0.5 seconds, and this project is 2.5 seconds because we're using less sophisticated equipment to detect EEG data, and 0.5 seconds is proven to be faster than eye tracking as well. And another important thing is this is gaze control, and it's not directly in sync with your eyeball movement. So some patients end up not having a perfect synchronization between their eyeball movements and looking at different targets. So for locked-in syndrome patients, this technique has a small advantage. And so yeah, they are different fields, but both have their own advantages and disadvantages.
Any more questions? In the back.
First of all, thanks for the talks. Very interesting. Quick question about the EEG processing itself. Since you're using wireless EEG headsets and you're using like you mentioned, it's basically based on ocular input, so to speak, to detect the frequency. Did you have any artifacts or any extra sort of snippets you had to filter out because of eye movement or because of perhaps the power from the wireless transfer between the headset and the computer?
I'm sorry.
Basically, did you have anything extra you had to sort of filter out or had to sort of clean out of your signals as a result of using a wireless EEG headset, or perhaps because of eye movements to begin with? Because I know that muscular movements in the face can actually induce changes in EEG signals, if I've understood correctly.
I'm sorry, I didn't get your question.
Don't worry. I'm basically asking if...
I'm not able to hear you, actually.
Oh, sorry. Okay. If people wearing the headset were to move their eye to look at the different parts of the screen,
yeah,
does that trigger any extra signal in the EEG spectrum.
Oh, okay, yes. So that kind of that's another type of muscular noise that ends up acting as an artifact to EEG. So these experiments are generally conducted where like the subjects are not supposed to like move the bodies in any way, and like any sort of hand movement or any sort of head movement would end up contaminating EEG signals. So it's expected to be as still as possible, and also like moving you need to move your eyes instead of moving your face. So the second you move your face, you end up creating more muscular noise. So these are artifacts, and these are like, I mean, several signal processing techniques have been explored to try and minimize these artifacts. Yes, these are one of the important challenges that are faced in improving signal processing. Yeah.
Last questions? Any more? At the back. Just to link up about what is comment, the 50 Hz kind of predominant that you found in your analysis, can it not be related to that, to kind of also other biosignals like heart rate and EMG, or any sort of also the predominant like 1 Hz kind of peak? Can it be linked to the fact that maybe the headset moved slightly?
I'm sorry, could you increase the volume?
Yeah, sorry. So basically, I was asking that if what he was talking about contamination of the signal because of other biosignals, can it not be because of the 50 Hz kind of predominant resonance in the spectrum, and also the 1 Hz cannot be due to maybe because the headset moved slightly, because in EMG, if you have like signals below the 10 or 5 Hz, is mostly because the device might have moved or something like that.
Yes. So that's an important point that you mentioned. Like you spoke about under 1 Hz, and the very low frequencies are related to motor movements, and so the thing is, in this system, anything below 6 Hz is noise, and anything greater than 9 Hz is, anything greater than 45 Hz is noise again, because you're analyzing up to 5 harmonics. So you're saying like the very low frequencies correspond to like hand movements and stuff like that, which actually should be eliminated, which should be filtered out. Okay. Yeah.
Okay. We'll call it a day there. Can I suggest for you, next time you do this talk, wear the headset and do something on the screen so you look at your screen to change slides. That would be that would be a good gimmick. So thanks very much.
Yeah, thank you so much.
One more big round of applause, please.
Thank you.